All right, welcome to calculus. So we're going to be looking at volume. How do we find volume? Well, this is probably a question you've been dealing with for quite a while, maybe since grade school even, of finding volume of solids. But this is a different approach than what we're going to deal with. Now, what I have in front of us here are a cylinder and a cone. Now, both of these objects, we already have equations that allow us to be able to find the volume of these things. But now we're going to be looking at, well, how can we do this in a different way? And the question of why we would want to do this in a different way goes back to the idea of these are regular shapes of sorts. But what if we're dealing with something that is terribly regular in terms of the cylinder? The cylinder is easily find the volume of. You find the area of that circle at the end, and then you just multiply times the length or the height, depending on your perspective of the cylinder, and you find the volume of the cylinder. So that's a pretty straightforward way of dealing with that. Why would we want to do it some other way? Well, because if we're not necessarily finding the volume of a cylinder, some other shape that is not regular, how do we do that? So let's use this volume idea right here as a starting place, the volume of this cylinder. So the idea, like I said before, the volume of that cylinder was found by doing the area of the circle, which I'll write as A sub c, times the length of the cylinder. Now we can further subdivide this up, right? So we can say the volume is pi r squared times length. Now, what's interesting about this aspect of it is essentially what we're doing is we're taking the area and we're multiplying it times length. And if you think about this in terms of what we've done with integration is taking a whole slew of pieces and adding them up. So if we think in terms of Riemann sums, we essentially took a bunch of lines and added all the lines together, and we got an area. So what if we were to talk about doing the integration of an area? Wouldn't that give us a volume? Which is exactly what we're going to do. It's this idea of taking and looking at this object and thinking about how can we split this up in such a way that we can actually deal with this and find the volume based upon some other quantity of some sort, right? So how can we look at this? What are the different ways? So what we want to do is we want to be able to take this object and set it down on a XY axis here, right? So if we're setting this down on an XY axis, what does this shape look like? Well, it depends on how we cut it and how we place it and which direction we place it and all that other stuff, right? So let's just think about it being like this, okay? Let's look at the shape looking just like this, and we're going to say that we cut through this cylinder sideways, kind of. If maybe from the camera perspective, you cut straight down on it, or you cut straight across from it, or any angle you want to on this thing. When we do that, what we end up with is a rectangle, right? So the idea of splitting that, cutting through that cylindrical loaf of bread, if you will, those slices long ways would give you a rectangle. So once we have this set up, well, then that's a pretty easy discussion to have, because you're essentially talking about a vertical line. So this would be x equal to, say, 2. And then we have a horizontal line, and this might be y equal to, say, 6. And again, these are measurements I'm kind of making up here. And of course, this would be x equal to negative 2 over here. But I'm not going to worry about that side of that, because what we can then do is we can take this piece right here, just the right-hand side of it, and I'm going to call this region 1, and I'll call this region 2, separated by the y-axis. Region 2, I don't need to deal with, because what I can do is I can just take region 1, and I can rotate it around the y-axis, and I will get my cylinder, all right? So that's the idea. That's the basics of what we're dealing with in terms of this process. So all we need to do is identify that radius. Now, I drew that radius out. It's not necessarily exactly 2 all the time, is it? Or is it? So let's think this through for a second. How do we start talking about this? Well, if you remember a second ago, we talked about the idea that the cylinder here we're going to cut it this way and we get those circles. And we start stacking all those circles together and we get the cylinder itself. So what I did here is I set this up so that when I rotate this around, I'm rotating around and I can create in 3 dimensions this cylinder. Right? So if I were to stand the paper up on end and look straight down at the paper, which I can't do, of course, I would get, if I were to stand this up like that on the paper, I would get that looking from above, right? So that's the idea of what we're doing here. So we took the cross sections, we rotate the cross sections, and now we get that shape that we're wanting. So there's that radius, and that radius goes from the center of that cylinder out to here, okay? So in this particular instance, that radius is, well, it's 2 at all times, isn't it? The radius to that outside edge of our object. We're going to look at another example here in a second, probably in the next video, that isn't necessarily always the same in that direction. So how do we find that area and then stack them all up? Well, we're going from here where y is equal to 0 all the way up to here where y is equal to 6. So there are independent pieces of this from 0 to 6 of the area, which in this case is actually pi r squared dx. Actually, it's not dx. We're used to always writing dx there, aren't we? But this one's not dx. This one's actually dy. Why is it dy? Because these are the y values that we're stacking. We're stacking from y equal to 0 to y equal to 6. So the y's are the ones that are changing, not the x's. So we need to be doing this integration with respect to y. Now everything still is the same. We haven't changed anything. All right. In this instance, the r value is 2. So we're doing integration from 0 to 6 of pi 2 squared dy, which means that, well, this is 4 pi, isn't it? So that's the integration from 0 to 4 of 4 pi dy. So that's 4 pi y, which has a fun ring to it, doesn't it? From 0 to 4. And that means we're doing 4 pi times 4 minus 4 pi times 0, which gives us 16 pi units cubed, okay? Because we're now dealing with volume, we're not dealing with area, so it's going to be units cubed there. Well, if we go back to the original equation for a cylinder, the original equation for a cylinder was pi r squared L. So in this instance right here, that would have been, I skipped, this is 6, right? 6, so that's not that, so that is 6 there, so that's 24 pi, my mistake. So this up here is going to be, if we use the original equation that we're used to dealing with the cylinder, that would have been pi times 2 squared times 6, which would be 24 pi units cubed again. So we get the same answer. You say, well, we did it much more complicatedly than we were used to doing it. Maybe on that one. But let's take another look at another example. All right. Let's think about y equals x squared as our equation, which looks something like this. What happens if we rotate just from 0, let's say 0 to 4 here, what if we rotate just 0 to 4 around the y-axis? What we end up with is a solid that looks something like a bullet tip, if you will, or a bowl that hasn't been hollowed out yet. Something like that, right? It's some type of bowl-looking solid cone. Well, not quite a cone yet because it's got a curved into it rather than a pointed into it, doesn't it? So we can identify all these spots. So this is, of course, didn't draw on to scale here, but we're going, I guess actually we're going up to here, and that'd be y equal to 16, right? So we're rotating it around this way. And the thing is, in this instance, we have all these little circles that we'd be finding. So when we find that radius there, it's still a circle. So we're still integrating pi r squared d something from a to b. And of course, these a to b's need to match up with this variable, whether it's x or y here. We'll talk about that in a second. But what happens with this one? Well, that radius is changing. It's changing with respect to that curve of the parabola there. So what's that distance from here to here? Well, in this instance, it's actually a distance of x, right? But it changes because the next one would be there's another x. That's x sub 1, that's x sub 2. That last one, of course, we would know, but we'll just call it x sub 3 for right now. But that's not taking into account the equation at all. Keeping in mind, well, we'll come back to that. Let's think of this through. So how are we stacking these circles, right? They stack one on top of the other according to the y-axis. So I'd actually be doing pi going from 0 to 16, because I'm stacking according to y's, which means I need to be doing dy, because the y's are what are changing. Oh, so that gives me some inkling about this x piece, doesn't it? I can't be using x's here because this equation that I'm going to stick in right here, that's going to be the r, because that radius is constantly changing, is going to have to be in terms of y, because that's what my dy, my d is here, my dy. So how can I rewrite this in terms of y? We'll go back to my equation here. The square root of y would be equal to x. All right, I'm not even worried about the negative version of this because I was only rotating from 0 to 4 anyway. And when I rotate from 0 to 4, it creates the other side. It creates this solid all the way around. So now what I need to put in here is the square root of y. And there's my equation, all right? So then I would be doing is square root and square root cancel. So I got pi from 0 to 16 of y dy, which means I need to do y squared over 2 evaluated from 0 to 16. So that gives me pi times 16 squared over 2 minus 0 squared over 2. So 16 squared was that 256, I believe. And then we divide by 2. So that would give us 128. So this is 128 pi units cubed. And what we just did there is called, and I always call it the washer method, but it's also, what we did there was the disk method. And washer is what we're going to be working with next, washer method. And it's really the same method. The washer piece just has an additional part to it that we're going to have to deal with. But there is the disk that we did. We had individual disks that we cut across, and if we stack those disks up, just like we would on anything else, we end up with that volume for that object there. All right? I hope you enjoyed this. I hope this was useful. Please reach out with questions and comments and your need for additional videos. Take care.